Oh, Jeremy?
Hello.
See. Oh, Christian, Gordon, Curtis.
Dark Church.
Okay. We have the homework 11. That's due. We said April 28th, correct? Did I say that last time or did I not? I don't remember.
Yeah, next Wednesday. Yep.
So that'll be the last homework. We have made good. Okay. Final exam is 2:45 to 4:40. Okay. So we did most of the necessary derivations for a simple antenna. So let me quickly recollect what we did. First of all, what is radiation from a source? Radiation is the part of the electromagnetic wave which survives even at r tends to infinity, and it has a 1 over r potential and the magnetic field associated with that, c times magnetic field, so that we can have the dimensions of electric field. Then electric field and velocity times magnetic field is the same. That's given by minus r hat crossed with mu naught over 4 pi. Let me put a c there. But this quantity has the dimensions of resistance. And then there is 1 over r e cubed r prime. And that's the same 1 over c. I'm canceling out d by dt prime. And one way to produce radiation is by changing currents. And the formula is given by this, like, plus r hat with r prime over c. Main characteristics comes from this piece here, r hat times r prime plus over c. So that's a good thing to realize. And what else? There's a 1 over r dependence here. This whole thing has the dimensions of current, so that's a good point to realize again. So it is an effective current, you can, if you want to say, but that is a change in the current that is contributing to that. The electric field is got by minus r hat crossed with the magnetic field, and it is also good to point out that, let me point that out here, c times b is also r hat crossed with b. And these three vectors, electric field, magnetic field, and the direction of propagation, form an orthogonal set of three vectors. And that's a characteristic of an electromagnetic wave, which is basically here we have derived that relation. We were doing a simple antenna, so we considered a very simple situation. It's pretty much an idealized situation. but still it captures a reasonable amount of details of a simple, of a very trivialistic antenna, if you will. So, and what we were talking about is we just have one long wire and we have a current in it which is sinusoidal. So this is L over 2. So this is length L, let's say. And this is right at the origin. And if you have this to be your z hat axis, and the observation point could be at an arbitrary point, somewhere very far away again. And that's angle theta with respect to that antenna. The current density due to this, prime T prime would be, let's say I naught. First of all, there is a direction that's in the direction of z. So that's z hat times I naught sine of omega naught t. So there's a sinusoidal oscillations in there. And that is delta t prime, let's say x prime, delta y prime, and step function which says that z prime is within a certain region. Usually there is also what is called a center fed antenna, where this current, notice what you're saying is that independent of where you are on this wire, the current is exactly the same, which is slightly hard to achieve. More realistic would be that it keeps changing around the wire. So you can add in those features, but that is making the antenna more detailed. But this is the simplest antenna where the characteristic is only by the source of the or the frequency of the oscillation of the current, which gives you a wavelength if you want, and the length of the wire. So there are only two parameters in the problem: the frequency with which you're oscillating the current, which is having an associated wavelength, and the length of the antenna. And the ratio of this will characterize what kind of radiation you get. And we showed that last time that the magnetic field associated with it, and once you get the magnetic field, you know everything else, correct? So that's equal to, we said, what was it? What was it? Let me see. Yeah, so that is going into the same form as we have it there. That's r hat crossed with mu naught over 4 pi. All that remains the same. That's the character of the radiation itself. And that integral we could completely perform. So that's a z hat. And that is c times I naught. So I can write the mu naught c there, right? So it's I naught times cosine of omega of t minus 2 pi omega naught r over c, and that is 2 times sine of pi l over lambda naught times there's one thing more, cosine theta over cosine theta. I think that's what we had, and that's visible on the board. Okay. Based on this, we calculated the power that's emitted into the solid angle, and we also averaged out the time dependence. So this is an oscillatory part that's sitting in here. So we average that out to basically get a factor of half in there, and we showed that the power per unit solid angle is equal to the normalization factor of 4 pi that is kept separately because solid angle is 4 pi, right? So it's kind of a fraction of how much power, how much of the solid angle we're talking about. Mu naught c over 4 pi, that's the resistance, times I naught squared. We called this P naught last time. And this came out to be, then there was a factor of sine square theta And sine square theta came from r crossed with z hat, right? So that's a sine theta. So when that we averaged out cosine, but that gave us a factor of half. But then the square of this also had a factor of 2, and overall what we had is 4 pi, and this is 2 times sine square of pi L over lambda naught times cosine theta over cosine square theta. Correct. Does that match with what you have, what I wrote last time? Can one of you guys confirm? Anyone? No?
Yeah. Well, the 2's gone.
2. This one?
Maybe I'm wrong. Hold on. Yeah, I think we're missing a 1/2 somewhere because we had, or no.
Because there's a 4 pi here.
Yeah, that's where. Okay, that's where it went. Never mind.
Yeah, so maybe I wrote it as 2 pi earlier. Anyone else? No?
Yeah, I think it's right still. Yeah.
Good. Okay, so yeah, so that's what it is, and we did one thing immediately last time, which was relatively easy, and let me just summarize that. And that is when the length is small, right? When L is very small, that's an extreme limit. So when I say small compared to what, if I have a wavelength associated with the frequency of oscillation of the current, if it is very small compared to that, so this is a small antenna, right, relative to the wavelength. In that case, this angle here is small because cosine theta doesn't go more than 1. L over lambda naught is small, so sine of a small angle is the angle itself. So cosine cancels out, and we showed that dp over d omega in that case. Oh, by the way, I think I used the p bar there, right? That's the average out. So this is p bar is equal to 1 over 4 pi. I call this p naught. And then this was sine square theta times 2 times pi L over lambda naught square. Interesting piece is that this is proportional to the square of the length over lambda naught. And in fact, we could integrate with angle also. So if you collect all the power here, P bar is equal to, if I add up all the angular dependence in here, this came out to be P naught times, it depends on this pi L over lambda naught factor. And if I remember correctly, it was 8 by 3. Okay, let me know if there's a mismatch there. Okay. Again, what we want to remember at this point is that it depends on the square of the length, right? As the total power is proportional to the length square, or the ratio of the length over the wavelength. Now let's do the opposite limit, right? So this is a good, nice, and we do the other extreme limit. So let's notice that what happens. First of all, as you increase the length, here earlier when length was small, if this is less than 1, this will never go beyond a certain angle, and this will always. So let me do this, spell this better. So let me go to the other. So we have this characteristic sine of pi times L over lambda naught times cosine of theta. Cosine theta is always less than 1. If L is less than lambda, for L less than lambda, L over lambda naught times cosine theta is always less than 1. So this never touches pi. And if sine of an angle doesn't touch pi, that means it never goes to 0. So that means for every angle, there will be a power radiated. It never goes to 0. But the moment I cross L lambda naught, if L gets greater than lambda naught, then there is a chance that this might become 0. That means power will go to 0 somewhere. And let's ask, where does that happen? So pi times L over lambda naught times cosine theta. When does it become 0? That is whenever this whole angle is a pi. So the first time it becomes 0. So think of the situation as you're increasing L. This gets larger and larger, and there's a chance that it can become a pi. So that will happen whenever cosine theta is equal to lambda naught over L. That means angle theta is cosine inverse of lambda naught over L. So at that particular angle, radiation disappears suddenly. So a diagram helps here. So move that. So we have a antenna. Right, that's our antenna, and this is an observation point. Right, that's your angle theta. And as you increase your wavelength, if you were to plot radiation, in the earlier case, this would have been just everywhere there would have been a radiation except theta equal to 0, and it would be like this. So you will plot this like this. So this is called a polar plot. That means to say the radius here tells you what's the intensity of the power. So when angle theta is there, theta equal to 0, that's 0. As you increase, it increases, and then you come back. So that's a polar plot. But in as L increases, there is a chance that, in fact, for a very large L, there could be a 0 like this. In fact, there could be another 0. There could be another 0, and so on. So these are called lobes, right? So there is radiation emitted in this direction, there is emitted radiation in this direction, but then somewhere in between there is no radiation. So if you're standing here exactly, very far away from this antenna, you won't get any signal. Think of a cell phone signal, and if you use such an antenna to transmit your cell phone signal, right there you won't get any signal. But here there is a lot of intensity. So let's actually calculate this. So we would like to know for large L what happens. So we are going to see that this gets more and more intense in the direction perpendicular to the antenna. So there is an orientation dependence in there. So the signal gets very oriented. So let's ask what happens at L very large, right? We would like to get this more precise in a sense. So let's consider the scenario where L is very large compared to lambda naught. It's a large antenna. Going back to our equation, so then basically we cannot make that approximation anymore. So we have to deal with the whole expression, and this is let me write this as the omega over 4 pi times p naught times sine square theta times 2, not much just copying here with the idea that we will integrate. Let's integrate this whole expression, the total power. And what we want to actually ask is how much power is emitted in total and how much power is emitted in the small region perpendicular to theta. So in one lobe, we will call it how much power is emitted. That will give us a measure of how much energy is thrown into the angle pi by 2. So first let's calculate the total power. Total power will be integral. So integrate this out. There is no phi dependence, so that immediately gives us a factor of 2 pi. That cancels and gives you a 2, and that 2 cancels out, so we are left out with P naught and 0 to pi sine theta d theta sine square theta and sine square pi L over lambda naught sine theta. We just now realized that there is a lot of radiation for this antenna in the angle perpendicular to the rod. So it seems like this is the nice direction. So let's actually call this angle chi, right? Chi is pi by 2 minus theta. So let's replace everything with that. So chi is equal to pi by 2 minus theta. That means the chi is equal to minus d theta. That's just so that I can center it around that chi. Just a small change of parameter here. So that's P naught. When theta is equal to 0, chi is when theta is equal to 0, chi is pi by 2. And when theta is equal to pi, it is minus pi by 2. And d theta then is minus of d chi, which the minus sign can be used to reverse the limits, and rest everything remains the same. So this is cosine of chi, all the sign becomes cosine and cosine becomes sine, right? That's what happens when you change pi by 2 minus theta. So this is cosine square of chi. This remains the same, but the argument now becomes sine of chi. Basically, all the cosine becomes sine except for this sine expression. Okay, with that taken care of, let us make a substitution in the argument of sine, because that's what decides when this goes to 0. Right? So let's make this to be z. That's just a substitution. I just called it z. We are integrating over chi, so we want to differentiate this. So pi, let's do that here, pi L over lambda naught. Cosine of chi d chi is equal to dz. But this already exists in our integral. So the total power emitted is equal to P naught. Limits are minus pi by 2 to plus pi by 2 when chi is equal to minus pi by 2, when z is equal to minus pi L over lambda naught. And that's plus pi L over lambda naught. That's our limits. Cosine chi d chi, that's dz over pi times L over lambda naught. Cosine square chi is, I write it in sine square chi, right? So that's 1 minus sine square chi is z over pi L over lambda naught. That's squared. Right? Why? Because this is, we have cosine square phi, which is 1 minus sine square phi, and sine square sine phi is z over pi over L naught. So that's cosine square phi taken care of. And then we have sine square of z. That's a simplification. That was why we substituted that. And divided by sine square phi, which is z square. And then there is, let me write that as z over pi L over lambda naught whole square. So that's an explicit substitution. One feature comes out immediately, and that's that one of these pi's cancel with that. It goes to the numerator, and I get L over lambda naught. Notice there is a linear L dependence, not a quadratic dependence, unlike earlier. For small antenna, it was a quadratic dependence in the length, and now it's a linear dependence in the length. Rest everything remains the same. So like this. But very soon, this is dz sine square z. Or let me write this as sine of z over z whole square. And there is a 1 minus z square over pi. That's your total power emitted. That's a harder integral to do, but we can take the limit for L very much larger than lambda naught. You can as well say that L over lambda naught tends to infinity. So let's say L is about 10 times larger than lambda naught. That means to 10% accuracy, that's infinity, but it could be made larger also, right? If it is 100, then it's 1% accuracy. In that case, this integral significantly simplifies, but still a little work needs to be done to evaluate it. So let's P bar is equal to P naught. This constant. And we have minus infinity to plus infinity uz sine of z over z the whole square. Notice that if I'm saying L over lambda naught to infinity, that is 1 over infinity that goes to 0. So that's it. That piece goes away. And that integral can be written in terms of one thing I will need to use is 0 to infinity. Let's say 0 to infinity, or I can say minus infinity too, because it's sine z over z is actually pi by 2. This can be done in various ways, but one of the, it is a little hard to evaluate that using trivial methods, but one of the ways is contour integrals, and that's, so we will use this as an identity, but still one has to show that from this you can actually reach it. But to go from here to there, that's easy, but this I will use as an identity, right? So this is, let's say P1. I don't know whether I've used this before or not anywhere else in the course. With that, so we just have to show that this integral can be converted into the other one, and that's P naught times pi. This can be written as, first of all, this is a square, so it is 2 times 0 to infinity. In z, that is 1 over z squared, and you can say that that's the same as d by dz of 1 over z will be 1 over z squared. So that gives you minus sign. So you put in a minus sign explicitly there. And then you say that's sine squared. That's a trick to evaluate that integral. Now use integration by parts. You put it on the other side. So that's 2, and let me open the brackets here. So there's a minus sign here, and make this a total integral in z d by dz of 1 over z times sine square of z. That's it. So that's contributes only at the limits, but this is not exactly the same as the above, right? So you want to subtract something out, which is equivalent to adding in this case, 0 to infinity dz 1 over z, and put the derivative on the other piece. Okay. In the board? Yes. This contributes only at the limits because this is a total derivative, and at 0, sine of z is equal to 0, and at infinity that is 1 over z that goes to 0. And also notice that at z equal to 0 there is a sine z over z, right? That goes to 1. Remember that sine z over z in the limit z equal to 0 is equal to 1, right? So it doesn't really go to infinity. So the limiting cases both goes to 0, so that whole thing goes to 0. And what we have is just the second piece there, E naught times pi times L over lambda naught times factor 2. And this is 0 to infinity dz. And we have 2 times sine z cosine z over z. Which can be expressed in this form. So that's sine of 2z so 0 to infinity dz sine of 2z over z. Substitute 2z equal to t, but then that will have a t. This z can be converted to 2 to z, nothing happens, and this is exactly equal to pi by 2. So what we have is this whole thing is p naught times pi L over lambda naught, and we have 2 times pi by 2. Again, the main difference here from the small antenna was that small antenna went a square of the length, and here is a linear in length. So if you had to design this in your lab and just changing the length, if you had to plot for various lengths, you should be able to see this square dependence and the linear dependence. So that's one nice thing in there. But we also said that this is very angular and very oriented, right? At theta equal to pi by 2, that is significant more radiation than the other than the complete of that for the small angle. So can we capture that also as to, for example, we can ask how much of the radiation is actually in the first lobe. So let's ask the following question. So if the radiation was here like this, that could be your first lobe, and that could be the second lobe in there. And there could be more radiation in there. So we can ask, first of all, what is this angle? What is the theta max for the first lobe? And how much radiation is going into that? Theta max is got by pi times L over lambda naught, and cosine of theta max is exactly equal to pi, right? That's the first time the argument of the sign in the expression actually goes to pi. So theta max is equal to the sine inverse of lambda naught over L. we have been working with chi, so let's immediately, if we are interested in chi, you would say this is pi times L over lambda naught times sine of chi max. Yeah, it shouldn't be called theta max, but I'll keep it as it is because theta goes from 0 to 1, right? So it's not the maximum value for theta there. So in this case, this is more appropriate to say it is the maximum value for the first lobe. And this gives you chi max as or sine of chi max, let's say, is lambda naught over L. Okay, so what's the power radiated? So power that's radiated in the first lobe would be equal to P naught times, how will I go about calculating that? So I will go from chi max, or chi max minus chi max to plus chi max. And that is, yeah, and this is d chi, cosine of chi, and cosine square of chi, and rest everything stays the same. And this is sine square. And the ratio of this, so let me call this is not the total power, this is one lobe, right? That's a power emitted in one lobe. Make the same substitution as we did earlier. Let me, yeah, this is better. I can see the screen better. Okay. So again, make the same substitution of z is equal to pi times L lambda naught times sine of chi. dz is again pi L over lambda naught cosine chi d chi, everything the same. But now the limits are different. When chi is chi max minus chi max, sine of chi max is lambda naught over L. So this is exactly pi. So instead of going from L over lambda naught, so this goes from minus pi to plus pi. That's the change in here. And this will be dz over pi L over lambda naught. Cosine square chi is 1 minus sine square chi. So first let me write this. So sine square of z, and this is z over pi L over lambda naught square. And that is 1 minus sine square. So this is z square over pi L over lambda. Let us again consider the limit where L is very large so that this can be neglected. So we are asking for a large antenna, how much energy is going into the first lobe? First lobe with that plot. So power radiated in the first lobe is equal to, again, naught comes in. This is again a squared integral, so that's 2 times pi L over lambda naught. And the only difference now is that the integral goes from, this 2 is because I changed minus pi to plus pi to 0 to pi. And the only difference is instead of going from 0 to infinity, we are going only from, let me write this, same integral, but this time we go only till 0 to of pi. So just here, so just to put this in perspective. So this is P total will be P naught 2 times this is 0 to infinity. Right, and we showed that this integral was pi by 2. If we take the ratio of this, that should tell us what fraction of energy is being thrown into the first lobe. So P1 lobe over P total will be equal to this. These coefficients cancel out. This is pi by 2. So this is 2 over pi when I invert it out there. And I have to do this integral. But it turns out that this integral is not easy to do. But you can do this numerically, right? So you can do a numerical code to do this integral, not very hard. And it comes out that this is about 0.9 to 1 sig-digit is 0. I mean, it's very easy to get more exactly. What it means is that 90% of the energy, if it is really thin, so there are many lobes here of radiation. So lobes, remember, is in the polar plot, how much energy is going in what direction. So that's your antenna direction. But most of the 90% of the energy is in a very thin angular cone perpendicular to the antenna. And that should give you an idea of how you can actually concentrate your energy in a certain region. But of course, sometimes if you're designing a cell phone antenna, you don't want to do that because only few people will get that. So you want to have another design for an antenna. So that's pretty much what this is. What you could do, for example, just for extending this, how you could extend this is, you have one single antenna here. We can, and of length L. One could talk about what if you had two antennas. Right? Again, same length L, but now let's say you have a distance A between them. Now what happens is that, yes, of course, there will be two such intensities coming out, but the radiation from each could interfere, right? If this A is small enough and it is close to the wavelength that we are using, then there could be interference effects coming in, and that can be easily analyzed. Once you have two, you can do three, right? And so on. Right? You can make a whole set with very specific characteristics, and one could ask, how does it change these patterns of radiation? But that we won't do here. But if one is interested, one could analyze that. And at this point, I will stop here. And next time we will talk about, now we are talking about angular distribution. Next, we want to talk about the frequency distribution. This is good that we have an angle dependence here, but what is the frequency dependence? How much frequency goes in a particular bin? So is it selective in frequency or not? So we'll talk about that. That's all. Thank you.
Thank you. See you next time.
Thanks. Have a good weekend.
Enjoy.
Have a good weekend.
Hmm.